and motion. Motion graphs are an important tool to use to show the relationships between position, speed, and time. For example, meteorologists use graphs to show the motion of hurricanes and other storms. A graph can show the location and speed of a storm at different points in time. The graph can be used to help predict the path of the storm and the time when it will reach a certain location. Imagine you are helping a friend who is training for a track meet. She wants to know if she is running at a constant speed. You mark the track every 50 meters. Then you measure her time at each mark as she runs. The data for your experiment is shown in Figure 310. This is position versus time data because it tells her position at different points in time. She is at 50 meters after 10 seconds, 100 meters after 20 seconds, and so on. To graph the data, you put position on the vertical y-axis and time on the horizontal x-axis. Each row of the data table makes one point on the graph. Notice the graph goes over 10 seconds and up 50 meters between each point. This makes the points fall exactly on a straight line. The straight line tells you the runner moves the same distance during each equal time period. An object moving at a constant speed always creates a position versus time graph that is a straight line. The data shows your friend took 10 seconds to run each 50-meter segment. Because the time was the same for each segment, you know that her speed was the same for each segment. You can use the formula v equals d over t to calculate the speed. Dividing 50 by 10 seconds tells you her speed was 5 meters per second. Graphs show relationships between variables. Physical science is all about relationships between variables. Think about rolling a car down a ramp. You suspect that the steeper angles on the ramp will make the car go faster. How do you find out if your suspicion is correct? You need to know the relationship between the variables, angles, and speed. A good way to show a relationship between two variables is to use a graph. A graph shows one variable on the vertical or y-axis and a second variable on the horizontal or x-axis. Each axis is marked with the range of values that the variable has. In Figure 311, the x-axis single angle has values between 0 and 60 degrees. The y-axis time has values between 0 and 3 seconds. 0.3 seconds. You can tell there is a relationship because all the points on the graph shall follow the same curve that sloped down to the right. The relationship between variables may be strong, weak, or no relationship at all. In a strong relationship, large changes in one variable make similarly large changes in the other variable, like in Figure 311. In a weak relationship, large changes in one variable cause only small changes in the other. The graph on the right below shows a weak relationship. When there is no relationship, the graph looks like scattered dots. Below, left, the dots do not make an obvious pattern, a line, or a curve. Scientist, a graph is a language that shows the relationship between two variables. Graphs are drawn in certain ways, just like words are spelled in a certain way. The first rule in drawing a proper graph is to choose which variable to put on which axis. Graphs are usually made to show a cause and effect relationship between two variables. A graph makes it easy to see if changes in one variable causes changes in the other variable. The effect. The variable that causes change is called the independent variable. In an experiment, this is the variable that the experimenter is free to change. By agreement among scientists, the independent variable goes on the x-axis. In the example below, mass is the independent variable, so mass goes on the x-axis. The dependent variable shows the effect of changes in the independent variable. The dependent variable goes on the y-axis. In the example, temperature is the independent variable and therefore on the y-axis. Like many rules, there are important exceptions. Time is an exception to the rule about which variable goes on which axis. When time is one of the variables on the graph, it usually goes on the x-axis. This is true even though you may not think of time as an independent variable. Suppose you measure the speed of a car at 4 places on a ramp. Can you figure out the speed at other places without having to actually measure it? As long as the ramp and car are set up the same, the answer is yes. A graph can give you an accurate answer even without doing the experiment. Look at the example below to see how. The students doing the experiment measured the speed of a car at 20, 40, 60, and 80 centimeters. They want to know the speed at 50 centimeters. Start by finding 50 centimeters on the x-axis. 2. Draw a line vertically upward from 50 centimeters until it hits the curve that fits the points that were measured. 3. Draw a line across the horizontally to the y. 4. Use the scale on the y-axis to read the predicted speed. For this example, the graph predicts the speed to be 76 centimeters per second. You will get the best predictions when the graph is big enough to show precise measurements. That's why you should draw your graphs so they fill as much of the graph paper as possible. A graph is a simple form of a model. Remember, a model is a relationship that connects two or more variables. Scientists use models to make and test predictions. Use position versus time graphs to quickly compare the speeds of different objects. Figure 3.12 shows the position of versus time graph for two people running along a jogging path. Both runners start at the beginning of the path, the origin, at the same time. Runner A takes 100 seconds to run 600 meters. Runner B takes 150 seconds to go the same distance. Runner A's speed is 6 meters per second, and runner B's speed is 4 meters per second. Notice that the line for runner A is steeper than the line for runner B. A steeper line is on a position versus time graph means a faster speed. The steepness of a line is called its slope. The slope is the ratio of the rise to the run. Visualize a triangle with the slope as the hypotenuse. The rise is equal to the height of the triangle. The run is equal to the length along the base of the triangle. Here the x values represent time and the y values represent position. The slope of a position versus time graph is therefore a distance divided by time, which equals speed. The units for speed are the units for the rise divided by the units for the run. The speed versus time graph has speed on the y-axis and time on the x-axis. The bottom graph on figure 3.13 shows the speed versus time for the runner. The top graph shows the position versus time. Can you see the relationship between the two graphs? The blue runner has a speed of 5 meters per second. The speed versus time graph shows a horizontal line at 5 meters per second for the entire time. On a speed versus time graph, constant speed is shown with a straight horizontal line. At any point in time between 0 and 60 seconds, the line tells you the speed is 5 meters per second. There's line on the position versus time graph has made a less steep slope. That means her speed is lower. You can see this immediately on the speed versus time graph. The red runner shows a line at 4 meters per second for the whole time. A speed versus time graph can also be used to find the distance the object has traveled. Remember, distance is equal to speed multiplied by time. Suppose we draw a rectangle on the speed versus time graph between the x-axis and the line showing the speed. The area of the rectangle shown below is equal to the length of time at its height. On the graph, the length is equal to time and height is equal to the speed. Therefore, the area of the graph is the speed multiplied by the time. This distance is the runner traveled. Pause here and answer these questions.